So as it turned out last week, Chong and I were preparing not the same slides, definitely not, but to talk about related things, and especially our joint project. So we had a discussion, we decided to keep it that way, but we take it from somewhat different perspectives. So to those of you who listened to Chong's talk yesterday, he were discussing 3 different situations with different kinds of localized vorticity. And I will more here focus on the kind of vorticity that makes this kind of wave possible that you see before you. And also the proof, how actually we construct this, because it is very different from the usual bifurcation down for steady water waves. So this is a joint project with Sam Walsh at the University of Missouri and Chong Zheng at Georgia Tech. And we're about to construct smooth stationary water waves with exponentially localized vorticity. This was just accepted in Journal of EMS. Okay, so what's the setting? We have water underneath a free surface. The unperturbed surface we put at x2, so the y variable at 1. And then there is a free surface, eta, just depending on x1. So this will be a 2-dimensional setting. The fluid domain is unknown. We look for it. And we will start from a flat bed. So actually, we did not start from that. So we tried for a few years with infinite depth, but as you will see, and some of you might recall from the talk yesterday, that was not possible with our assumptions. So this is the setting, but to make water waves, we need a little bit more, namely the Euler equations. Now, I don't write them in the velocity form here, but in the form of a stream function. So then the steady Euler equation reads as Laplace on the stream function psi is equal to gamma, the vorticity function, evaluated in imp psi. Then we have 2 kinematic boundary conditions. So the flat bed and the free surface are impermeable, so there are no particles leaving them. And I will come back to the choice that psi is the same, so the stream function, both the surface and the flat bed are streamlines, they have the same constants. So actually physically you only need them to be constants, but this is related to the finite energy assumption that Chongqing was talking about yesterday. And then finally, to actually have a wave, a free surface, the extra Bernoulli condition, which is nonlinear, and you might see that there is gravity, so the little g, and there is a capillarity with a strength alpha or alpha square, where little kappa is the curvature of the free surface. And what we'll add here, but this is not part of the mathematical problem, but we will search for a solution which has exponentially localized vorticity, which looks like this. The surface will actually not look like what I'm describing. So if, for example, Sam or Miles or Ming is in the audience, they will tell you that this is not the surface for this kind of wave, but this is the surface in the picture. Okay, the main theorem here is a lot. I will not go into the details now, and I will come back to it later, but I want to focus on 2 things for now. Namely, that we'll add some assumptions on the vorticity function, which I will come back to. And then there is a small dilation parameter delta. And if that is small enough, then we find a finite energy stationary solution to the water wave problem, which has the property, and if you look in the second blue box, that is very close in a Sobolev space, extremely close. It's e to the power -2 over delta to psi naught. And what is psi naught? Psi naught is a triple sum or combination of capital U's. And these capital U's are the ground states. And these 3 terms, you see, the first one, U, is the leading one, and then the other ones are very small, and they actually correspond to ghost vortices. I will come back to that. So we construct something which is very close to a capital U, which we will start with to construct our waves. Now, okay, so what kind of vorticity would you need to get a solution of the kind that I showed in the picture? So if you go back a few years, now it's actually more than a few years, but to 2004, the first large rotational steady waterways were constructed by Adrian Constantin and Walter Strauss under the general assumption of no interior stagnation. So in particular, the horizontal relative velocity, u minus c, would never be zero. So there is no single particle traveling with the same speed as the wave. Now, if you don't have any vorticity, so you just have a running stream with a parallel transport, and up on that comes a wave, then there are no closed streamlines or no critical layers. So you don't have stagnation within the fluid. Okay. Now, what is the next step? The next step is to take constant vorticity. But what does constant vorticity mean? So constant vorticity actually means a linear background or affine background stream. So the background current is linearly shared, and it's exactly, or at most, depending on how you put up c, one point where the speed of an individual particle and the speed of the wave can be the same. So you can get at most one critical layer for constant vorticity. Now in 2008, I looked at the nonlinear particle paths and the linear theory for the critical layers. And Erik Wallén in 2009 then, based on this linear theory, but also extending it to the first exact proof for water waves with a critical layer. So that is in the case of constant vorticity, you get exactly one critical layer as most. Now, okay, zero vorticity, that's the first step, then constant vorticity, that's the next step, and you get one critical layer. If you go to linear vorticity, you might think, okay, so then I get something quadratic, but actually you get something much more, potentially much more rich and complicated. Because if you have a linear vorticity function, you essentially get that psi yy is equal to alpha psi, where alpha psi is the linear vorticity. And that has solutions of sinusoidal form. So you can actually get arbitrarily many critical layers, arbitrarily many points where the background stream has the same velocity as the wave itself. So if you have a linear or superlinear vorticity function, you don't only can get arbitrarily many critical layers, you can also get multimodal waves. So waves not just like a cosine, but a combination of several ones. And as we'll see now, also waves with more or less localized vorticity. So this picture is from one of my papers with Erik, I believe. And here are some, so this is just some numerical plots where you see two critical layers. So this is like linear or affine vorticity. And you see that there is a vortex in the middle, but then it's like stretched out, and then there is a new vortex because this is periodic setting. Now, you can ask the question, is it possible not to have these centers, these vortices connected? So actually to get something completely localized, so compactly supported vorticity. And as Jong-Chun then talked about a lot yesterday, he, together with Jalal Shatta and Samuel Walsh in 2013, constructed the first compactly supported critical layer vorticity solitary waves on infinite depth. A student of mine, Christopher Warholm, who had Sam also as a co-supervisor, did the finite depth case then with multiple point vortices. And Hang Le, who was a student of Sam and is a postdoc of me now, did a dipole in the infinite depth. So that you can do. So now we have several different things. We have that if you have, for example, an affine linear or superlinear vorticity, you can get arbitrarily many critical layers, like in periodic waves. And we have the compactly supported waves, like the ones in Jong-Chun's work and Sam's and Jalal's. And the question was now, can you construct something like in between these? So can you stretch out the periodic waves with critical layers or with one critical layer and have vorticity that is localized, but it's not compactly supported, but it's truly localized. And this comes back to the question that Walter asked yesterday, if you could get some limit. So, and you actually can. So it's, I will come back to in which sense it is a limit. But somehow we want to have waves that are localized, and as some parameter goes to 0, they essentially approximate point vortices. So how to do this? So I've done a couple of proofs on bifurcation for water waves, and a lot of other people have as well. And in all the proofs I've seen so far, in almost all the proofs I've seen, you start from a running stream. So there's a flat surface, and you start from that, and you bifurcate like continuously or even real analytically from that state. You could also start from a known solution, like an explicit solution, for example, like a Krappus wave or something, and you perturb it a little bit, but you have a solution. So we do not start from a solution on the water wave problem. We start from what could have been a solution if there was no surface. So in R2. So we take just the interior equation, so actually the Euler equation without boundary conditions, you could say, with some vorticity function gamma, and we go back to theory that has been done, so elliptic theory, that this semi-linear PDE problem, if you consider it in R2, then under quite general, I mean not completely general, but quite general conditions on the right-hand side gamma, then you can get a unique, radial, and exponentially decreasing solution in R2. So Walter, for example, has done work on this a long time ago, and many others as well. And this is the starting point. So this is definitely not a water wave, but it is something living in R2. And it looks like this. So now the question is, can we cut U? So, I mean, this is in R2, and there should be a flat bed, and there should be a free surface. So we need first a way to cut U in a meaningful way, so that it actually fits into the fluid domain. And then we need to find a non-trivial free surface that's actually a water wave. And there are several, so now I come into the proofs of how to do this. So the first thing, namely to cut U, to take away the part of U which will be outside of the unknown fluid domain, leads to the introduction of a boundary correction operator. So what we'll have to do is we'll have to take away the boundary values of U simply to get something that has 0 trace on the flat bed and the free surface. You can do that in many ways, but in fact, the way we do it is very much inspired from the kind of vorticity we have. And then we'll look for a stream function, which is the ground state, perturbed with this boundary correction to make it have 0 boundary values. But it's still not a water wave unless it also fits the Bernoulli condition for the free surface. Therefore, we add a little U, and that will be the unknown variable. But in order to do this, we'll need 2 parameters. We need a dilation parameter delta and a translation parameter tau, which I will show in the next slide. Now, I was talking a lot about different kinds of vorticities some slides ago. And one of the reasons for that is namely that the kind of waves we now see, they happen for like the next order of complication or complexity in the vorticity. So you could have like no vorticity, constant, then you could have linear, and this is like the next step. It's a perturbation of linear. So the vorticity function gamma is leadingly linear, so gamma of t is t plus something which is like big O t squared. It is more, it is not only that, so you need something else, but it's much more general than something specific. But if you want to think about it as t minus t squared. So it's leadingly linear, but it needs to cross the zero axis again. So it's linear with a smaller perturbation. And that is where these kinds of waves now will happen. Okay, so why should this work? Because we don't start from water wave. So we're sort of taking R2, we're cutting it off, and then just hoping, not just hoping because we proved it, but before there is a proof, you hope that this will work. So why does it work? One thing is the dilation parameter. So what we do is first we have a fluid domain which just has depth 2. So from -1 to 1 with where we want the vorticity to be concentrated in the middle. And we look for even functions. So at the origin, essentially, we should have the vorticity. But think about the capital U, the ground state. It's big in the middle, and then it decays exponentially, radially, away from that center. So what we do is we dilate everything. So we push the boundaries of the fluid domain very, very far out. So that in the new setting, the upper surface is approximately at 1 over delta, and the lower one at -1 over delta. So now the distance is 2 over delta, and delta will be very small. So when we say that this is a finite depth solution, it is true, but the depth is extremely, the depth is huge. It's not infinity, but we can only guarantee that we have these waves when delta is very, very small. Then there is a second parameter, the tau, which is the translation. So that translates the center vorticity from the origin slightly up, if tau is positive, or slightly down, if tau is negative. We didn't have that one originally, and then it didn't work. So the idea is, as I will show again, is that we use continuity. We will move the center for fixed delta. We'll move the center, and at the exactly correct place, we get the solution. Now, okay, so what is the problem here? So why is this difficult on a deeper level, and why does it work? So the ground state satisfies Laplace of u is gamma of u. Now, if you take the derivative of that one, then you see that the linearized equation, which is Laplace of v is gamma prime of v, it has at least two trivial solutions, namely the x1 of u and the x2 of u, just by differentiating in the solution you know that ground state satisfies. These will cause problems for us because they act as degenerate directions. They are kernel of the linearized problem, so that we cannot invert the linearized operator. But we will in that, but we cannot in R2. So one of these null spaces we actually nullify by searching for horizontally symmetric solutions. So the x1 of u is just because we look for even solutions, and u is even, so the derivative of it is odd, and therefore that one goes away. But the problem which will be with us all the time is the y derivative of the ground state, the x2u. But it's also what we use to project the whole problem onto a one-dimensional subspace, where in the end we'll be able to solve things. For now, it's a kernel. So for now in R2, we cannot solve there, but we still use it to project. So we take the equation we know, that one fulfilled by the ground state. Laplace of u is gamma u. We project it, so we just multiply with the x2u, that is allowed. And then we introduce just the primitive or antiderivative of the little gamma, of the vorticity function little gamma. So we take that equation, and now we integrate it over the fluid domain. So let's say that we had a solution psi or psi, which is essentially like the ground state. We integrate the little blue box. So that is just the equation fulfilled by the ground state. We use that the surface is a streamline, so we have 0 boundary values of psi on the upper and lower interfaces. So then we have 0 to the left by just solving this integral, right? Calculating this integral. Then we use, you will see the calculation soon, then we use some integration by parts and boundary conditions. And now we have a right-hand side and a left-hand side. The left-hand side is 0, and the right-hand side is essentially the surface integral of the absolute value of the velocity field squared with an outward normal derivative. It's at the surface, but it's also at the flat bed. So that means that if you have infinite depth, so there is no flat bed, there is only the surface, then the right-hand side for any non-trivial solution would have to be non-zero, but the left-hand side is 0. So this is like the argument or the proof actually that there cannot be any finite energy solutions on infinite depth. But on finite depth, you could have a balance between the surface integral and the flat bed integral in the right-hand side, so that they exactly take each other out, and you could get that this equality is satisfied. And the way we do it then is that we'll translate. So U is radial, but recall that there is not an absolute symmetry between the flat bed and the upper surface, because there is an extra condition, the Bernoulli condition on the upper surface. So that's why we cannot find a solution exactly in the middle, but we'll move about. So then the right-hand side will show that it can be positive, it can be negative, and the left-hand side is 0. So there is a hope of a solution by a continuity. So that's the idea behind it. So that's why it works on a deeper level, but then we have to do it. So we bring everything back to horizontal slab with two unknowns. One is we use the conformal mappings, but essentially we get that the surface is now called capital gamma S. That's in a Sobolev space, so that's the surface elevation. We need to find it. And we have little u, which is a perturbation of the boundary corrected ground state. And so that has 0 boundary data, and we'll look for that one. We will need very precise estimates. On the ground state, that is not so hard, because, okay, so first we did it ourselves, but other people have done it. But then actually the boundary correction operator is very important here, and there are commutators arising. So this was a large part of our work. And then we'll diagonalize the system in the end. So in doing that, we'll introduce an eigenfunction, which you could call like a Lyapunov-Schmidt reduction on some abstract level. It's not the standard Lyapunov-Schmidt, but on an abstract level, it's similar. And then we'll solve the 3 equations. So the surface condition, the Bernoulli surface equation, and then there are 2 from the diagonalized Euler. So these 4 steps are what we'll now do. Okay, so we have you have a solution of you have a ground state solution of the semi-linear elliptic problem in the whole plane, but you want to cut it to have 0 boundary data on the places where you look for the surface and the flat bed. Of course, you can just take away the value of u, whatever it is at that point, but we'll do it in a cleverer way. So recall that the vorticity function is leadingly linear with a small perturbation. Again, think of it as t minus t squared. And we'll use that behavior. So, namely, what we do is, if you look at the linearized equation, that is gamma prime of the ground state minus Laplace. What happens with gamma prime of the ground state as we come far out? So as we come to the free surface and the flat bed. Well, u is exponentially decaying, so it goes to 0. Gamma prime is like 1 plus OT or OU. So gamma prime tends to 1. So that is our guide. So the boundary correction operator is introduced as the solution of the elliptic problem. 1 minus Laplace of the boundary correction is 0 in the fluid domain, and it has the same values at whatever function you are, for example, u at the boundaries. So So that operator, I mean, you can even write down it on the Fourier side explicitly. So that is a very well defined elliptic problem which we can solve. And the good thing is that the boundary, so if you take U and now you take the boundary correction, not only does it have the correct boundary values, right? But it also is, as we'll show, essentially a reflection operator. So it sort of reflects you outside of the fluid domain, because we're cutting it off outside, into the inside, and then it decays exponentially fast because of the elliptic behavior of the operators. So that is the boundary correction which we will use, and it really helps us in simplifying a lot of the calculations. So we look for solutions which is the ground state minus this particular boundary correction plus a little u which is unknown. Okay, so then what is the system? Here it is. In the fluid domain, you have the Euler equations. That's the first line. So minus Laplace plus gamma prime of u acting on this little u plus some big F, which is like lower order or less important. Both. And then the second line, which is the Bernoulli condition, where the leading term is also an elliptic invertible operator coming from the capillarity of the problem, and then there is a capital G. Now, if you look at, I've written out what capital F is and what capital G is. Now, capital G looks horrendous. It's some horrible Fourier multiplier, but in the end, it's not that bad. So you can have control of it. I think it's zero order. I cannot check right now, but anyhow, you can get control over that one. But the real problem is really in the first line. So it looks so simple, like minus Laplace plus gamma prime of u. But the problem is that this in R2, this has a kernel. So we cannot invert it without really proving that something very good happens when we go from R2 to our fluid domain and project onto the correct subspace. So that is really that the x2u is a degenerate direction. That is what was bothering us for a long time. So G is not the real difficulty. You can invert Bernoulli, you can solve the Bernoulli equation, but controlling F and the first equation with relation to this kernel direction is hard. And all this, everything is exponentially small in the end, so that was a problem as well. Okay, what is good is that you can use different ways, like center and stable and unstable manifold methods, or maximum principle, or elliptic estimates, ODE techniques, to show things for the ground state. And these other people have done as well. And the good thing is you have very precise control how both the ground state and all its derivatives actually decay far out. In the middle, okay, U is just what it is. It would be the center of vorticity. Far out, it decays exponentially fast with a coefficient determined actually by gamma prime, which is 1. That's why you have e to the power r. Now, so that we didn't have to do, but what we had to do is calculate what happens then for our boundary corrections. So the u VC is not so hard. The dx to u VC, which also appears, is much harder. But the good thing is the boundary correction of the y derivative of the background state, the boundary correction there, it's just taking the values at the upper surface and the lower bed, reflecting them. So that's why you have 2 over delta plus c dot, plus something smaller. So it's really a reflection operator, and we prove that. And the good thing is also that it depends on the translation. So when we move the center of u a little bit up or down, the estimates for the boundary correction of the x2u, the degenerate direction, they change with this translation, which will help us to get the skewness in the boundary corrections. Okay, as I said, the singular direction of the y derivative of the ground state, the x2u, which is in the kernel in R2, that is a problem. But how do we get around it? Well, okay, we have this assumption on the vorticity, It's that it's leadingly linear with a small perturbation. It needs to cross zero at some point. It's a C2 function such that we have this radial solution, which is in C2L2. But hidden in A is that you need B, namely that the kernel of the linearized operator is really spanned by the two degenerate directions, dx1u, dx2u. This is guaranteed for a lot of gammas, for example, the t minus t squared. But we choose to write it in this way so you can actually check the two ones independently from one another. And as Chong-Chun mentioned yesterday, a lot of people did work on this. If you want to check the precise conditions to guarantee this, for example, you can look at the following references there. So this goes back to Lee and Nierenberg, Neat, Takagi, Rustic-Lyons, and then there are more modern versions as well. Now, the good thing is that on the perpendicular space of the generate direction, we have invertibility. That is guaranteed by the condition B. So that we have in R2. And then we prove that because everything is so small, far out, we also have it in the fluid domain, which we're searching for as long as its delta is small enough and it's not R2. So we have our invertibility in the complement of the difficult direction, in the orthogonal complement. So then we can do the Lyapunov-Schmidt reduction. We cannot work with the x2 directly because that comes from the whole plane and we're working with zero boundary data in the surface domain. So we take away the boundary correction of the degenerate direction. It's still not really good because that one is now not an eigenfunction for our problem in the new fluid domain. So we perturb a little bit. So we take U2, perturb the whole space, and we find an eigenfunction of the linearized problem. So U0 is essentially the difficult direction, but we have skewed it ever so little, and now it's an eigenfunction for the linearized operator minus Laplace plus gamma prime u. Now recall that the x2u itself is in the kernel, so it's an eigenfunction with eigenvalue 0 in R2. So that means little l, little l is very small. It's very small, and you can write it in this form, but this is an indefinite quadratic form. So little l was a big problem. For a long while, little l was a big problem. But the good thing is with it, you can diagonalize the system. So you get the difficult equation, which is the first one. So that's just on the span of U0, which is essentially the difficult direction. And there it's just a scalar equation. So it's little l plus some value should be 0. Now the only question is, can you get that to be 0 or not? The second one is the elliptic problem. So the Euler equation in the good perpendicular space where you can invert the semi-linear, the linearized operator. So that's good. And the third equation is the Bernoulli equation. So what we do is we solve, you can do this in different ways, right? But we solve the second one first. So we solve in the good complement of the difficult direction, we solve the Euler equations. We can do that for small surface, small delta, and small little u, which we search for. The Bernoulli equation we can also solve because of the capillarity, again, for small data. So then we can solve these, and it only remains the first scalar equation. And we calculated so much, and what we got is that, okay, little l is e to the power minus 2 over delta, and then the expression, the inner product with a capital F, is of the same size. And we try, and then can we get this a little bit bigger, a little bit smaller than that, but we couldn't. So what's the hope? Well, I mean, by now you've heard it several times, but it really comes from, so where does little l come from? Little l is an eigenvalue. It arises originally from inner products involving this degenerate direction, dx2u. But where is the x2u coming from? It's coming from the ground state. It's the y derivative of the ground state, and we're evaluating it far out. Now, how can you get one of the terms in the L plus in the product to be, well, how can you get the two terms to balance to 0? Well, what you can do is we can move the ground state so that the value of the derivative x2 u of u, x2 of u, becomes much bigger in absolute value at one point than the other, because u is big in the middle and decays exponentially fast away from the origin. So since u is radial, by translating in the tau, we can get leading terms in this scalar equation of the form that they are exponentially small. So they're like e to the power minus 2 over delta, essentially. Tau is extremely small. But they vary with the sign of tau. So if we go up, we get something positive. If we go down, we get something negative. We have to, I mean, it's not like just going up and down. We have precise thresholds for this, but essentially it's a sign here that saves us. And I'm suppressing a few details here, but I see that this was like if I had a lot of time, but I don't have a lot of time, so I will suppress that. So by doing that, we can get positive and negative, and we can get 0 in between. There is no guarantee that there is only one solution. Also, for a given vorticity function, there could be, depending on which vorticity function you take, it doesn't have to be a unique ground state. So you can construct several different waves from the same vorticity function. But coming back to the theorem now, what does it say? It says that if we just take delta small enough, so the water is very deep, but it's still finitely deep, but it's very deep. There exists a translation parameter, which is extremely small. So it's like e to the power minus 1 over 2 delta, where delta again is very small. And we have a solution which is very close to the ground state, corrected with the ground state's values far out. Now you can think, so someone asked me, so that was a very good question actually. So someone said, okay, this is like 3 vortices, because you have u almost in the center, and then you have u again up, and you have u again below. But it's the leading u, the first u in the expression for psi0, that is the big one. So that is the concentrated vorticity, it decays fast away. The two others have their center outside of the fluid region. So when they appear in the fluid, they are actually exponentially small. But this is a leading expansion, and then you see we can even more or less calculate the free surface from the ground state. There is a formula for it in convolution form. The vorticity is spiked, as Chong-Chun mentioned yesterday. So as delta is small, it gets more and more concentrated in the middle. So the L infinity norm of it actually explodes, while the L1 norm is finite. But the total vorticity is almost 0. It's not 0, but it's almost 0. So in some sense, these solutions, they do, I mean, the vorticity does converge in some sense to a spike, to point vortex, but it's just that if you do that when you converge, there will be no free surface anymore. So you're going out in all of R2. So you will converge to, which could have been a solution to the waterway problem if there were no surface and no flat bed, which of course is related to the fact that we're starting with such a solution, such a ground state. Okay, so I think that is pretty much it. Thank you for joining me.
Thank you very much, Matt, for your very nice talk.